What can this simple act teach us about quantum entanglement? Quantum entanglement describes what we call entangled particles. Particles can become entangled in one of two ways. The first is when they come from a common source, and the second is when they interact. If we imagine this phone as a particle, it can become entangled with another phone by either coming from the same store or by calling the other phone. When these phones become entangled, it is like they are connected by an imaginary string. It will keep them connected no matter how far apart they come. Their properties will be connected. Particles have what we call spin. A value of +1 is assigned to one spin, and a value of -1 is assigned to the opposite spin. For simplicity, imagine that this spin is like that of any other rotating object. If these were normal particles, they might be spinning up, down, to the right, to the left, or anywhere in between. However, when we look at these particles through a quantum lens, they exhibit a key principle in quantum mechanics: superposition. That is, they have every spin possible, not just one. To illustrate this, we can come back to the phone that I dropped. My phone exhibits quantum qualities and is now like Schrodinger's cat, or more appropriately, Schrodinger's phone. I dropped my phone and it landed face down. At this point, I don't know if my phone screen is safe or cracked. What Erwin Schrödinger proposes is that until I pick it up and see, my phone screen is both safe and cracked. This is superposition. If we come back to our entangled phones, both of which have been dropped, each one will have its own superposition. Each phone will be both safe and cracked until it is measured. Looking at possible outcomes after measuring, both phone screens could be safe, both could be cracked, one could be safe and one could be cracked, and vice versa. There's a 25% chance each of these outcomes could happen. If a value of +1 is assigned to a safe phone screen and a value of -1 is assigned to a cracked phone screen, we can take a closer look into these possible outcomes. With entangled particles, their combined spin must equal 0. When in the superposition state, each particle's spins cancel out to equal 0. Because of the law of conservation of angular momentum, the spins must cancel out after they are measured as well. This allows us to eliminate the options where both screens have the same state, as that would result in a value of +2 or -2, not 0. We are left with two options that have a 50% chance of appearing. Now comes the cool part. Once we measure the state of one of the phone screens or the spin of one of the particles, the state or spin of the other one is immediately known. Recall that prior to measuring the state of the phone screens, they were both safe and cracked. After measuring, their state will become permanent, and the imaginary string that was connecting them across any distance will be broken. If the first screen is measured to be safe, it is permanently safe, and the other phone screen will become permanently cracked, instantly, no matter how far apart they are. With a particle, measuring the spin of one to be, say, spin up, the entanglement is broken and the other particle is immediately known and measured to be spin down. This seems crazy, and Albert Einstein thought so too. In fact, he called it spooky action at a distance. His theory of relativity places a speed limit on the universe, the speed of light. What quantum entanglement seems to suggest is that these particles are exhibiting faster than light communication. These particles seem to communicate instantly over great distances as to what their spin is, so the other particles will have the opposite. Einstein struggled with this and believed it had to be due to a local hidden variable. This would be like the particles had conspired when they were first entangled to have opposite spins. Because of superposition, however, particles don't have a defined or specific spin until they are measured. Therefore, Einstein claimed that quantum mechanics was incomplete, and there was some hidden theory that was preventing us from understanding. Niels Bohr disagreed. He argued that in the quantum realm, cause and effect cannot be combined with the concept of space-time. What this means is that because quantum entanglement is describing how knowing the spin of one particle causes you to know the spin of the other, space-time must be excluded. You can't think of the particles as communicating over a distance during a certain length of time, because although space-time and causality are complementary, in the quantum realm they must be thought of separately. Einstein may rest because the speed limit is still intact.